So, good morning again, everyone, and thank you for joining us. So, this is the eighth webinar of the Philippine American Academy of Science and Engineering. So, the Philippine American Academy of Science and Engineering, or PAASE, is an organization which consists of scientists and engineers of Filipino descent, initially from the Philippines and in the US, but now we have expanded and we have members from other countries as well. So, for today, it is a pleasure to introduce to you our webinar entitled Socio-Ecological Network Structures from Process Graphs. So our main speaker is Dr. Angelyn from De La Salle University. She is currently an associate professor in the Mathematics and Statistics Department and the Assistant Dean for Research and Advanced Studies of the College of Science. She joined De La Salle after the completion of her doctorate degree in systems biology at the University of Rostock, Germany. She held a research fellowship and two professorial chairs in mathematics, namely the Brother C. John Lennon FSC Professorial Chair in Mathematics and the Brother Albinus Peter FSC Professorial Chair in Mathematics. Several of her most notable publications include her work on establishing the first mathematical and compartmental models to describe and analyze the influence of the receptor sorla in the amyloidogenic processing of Alzheimer's disease. Her recent works apply bioinformatics and machine learning approaches to study and discover the patterns in the topological structures of the disease networks and to identify biomarkers associated with different diseases. She will be joined later by Professor Raymond Tan, also from De La Salle University, who is a well-known guru in process integration. So without further ado, Angie, you may begin the lecture.
A pleasant morning or day to all of you. So I'm Angie from De La Salle University. Together with Dr. Raymond Tan, we are excited to present our recent work on applying process graph to study the structural properties of socio-ecological systems that are represented as networks. So this work is done in collaboration with Professor Cabeza, Akos, and Professor Friedler. Preprint is actually available in bioRxiv. You may scan the QR code shown here in the slide using your phone to get a copy of the preprint. So the general outline of the talk is as follows. We'll start with a brief overview of existing modeling approaches applied to study social ecological systems, followed by an introduction to process graph, or what we will here on refer as P-graph. Then we will end this talk with our main result on applying P-graph in socio-ecological network systems. To start, I'll first define ecosystem. So it is a biological community of interacting organisms and their physical environment. So ecosystems services are essential to civilization or to the society. However, many of our activities, like the human activities that we have, are actually destroying the natural ecosystems. So this may cause deterioration of ecological services, whose value in long term dwarf the economic benefit that our society is gaining from these activities. Hence, it is very important to conduct appropriate actions in time in order to restore the functionality of many ecosystems. So one of the earliest and I think the most well-known ecological model is the predator-prey model. So predation is a relationship in which we have members of one species consuming members of another species, like shown in the illustration. Okay, so let's consider a situation between a fox and a rabbit. Okay, so foxes feed on rabbits and they are dependent on rabbits for their survival. On the other hand, without the fox, rabbit can actually survive by eating vegetables. Okay? But without the existence of the fox, they might end up being overpopulated. This somehow shows that the existence of both prey and predator are important in order to maintain a balance in the ecosystem. So the prey-predator model is first proposed by Alfred Lotka and Vito Volterra independently in 1920s, and it's now known as the Lotka-Volterra model. It has many generalization and application outside biology. So the model takes the form of a pair of ordinary differential equations, one representing the prey and the other representing the predator. So you have here the parameters representing the growth rate of prey, the rate at which predators destroy prey, the death rate of predators, the rate at which predators increase by consuming prey. So the first equation represents the change in the prey's population given by its own growth minus the rate at which it's preyed upon. Whereas the second equation expresses the change in the predator population as growth fueled by the food supply minus the natural death. Here we show the time series or simulation of the Lotka-Volterra model, where the two populations actually exhibit cyclic behavior. It can also be plotted using the solutions parametrically as orbit in phase-space or a phase-space portrait without representing the time. So we have one axis representing the number of prey and the other axis representing the number of predators for all times. Another popular approach of modeling prey-predator system is the agent-based modeling. So this approach not only includes the time aspect, but also consider the spatial aspect of the model. So the prey-predator system is not limited to two species. As shown here, it can be extended to a more complex prey-predator structure, like what is shown on the left side, okay? Or to even have a more complicated prey-predator structure. For example, this is an extended three-species food chain where the lowest level prey X is preyed upon by the mid-level species Y, which is preyed upon by a top-level predator Z. Here we present the ecological network analysis. It uses network theory to study the interactions between organisms or population within their environment. So it's represented by a network. It's predominantly concerned with the interrelations of materials and energy, represented by the F or the flows in the networks. Okay. So the components are represented by the X, okay? And the assumption of the system is that it can be represented as a network of nodes that are connected based on their relationship to one another. And in ecological systems, the connections are usually based on the flow of energy or matter, like water or nutrients, between the system's compartment. So here, A is the adjacency matrix. It's a binary representation of the connections between the components. It is 1 if there is a connection between the nodes and 0 otherwise. And then the intercompartmental flow for the network is represented by the flow matrix F. So given the ecological network, one analysis that can be performed is the functional analysis of the network. Okay? This is done through the structural path analysis, which enumerates the number of pathways in a given network. And this is the basis of the 3 functional analyses shown here. So one is flow analysis, storage analysis, and utility analysis. Each of these function analyses derive from the relationship of the flow storage data presented in the networks or in the system. Also, given in the ecological network analysis, or ENA, you can also perform structural analysis to determine the existence of some of the properties illustrated here. So for example, one may illustrate the existence of the property of dominance of indirect effects, where a system receives more influence from indirect process than the more. So basically this answers the question, is the system receiving more influence from an indirect process or than the direct process? And then you can also determine whether it exists the property of homogenization, whether an action, whenever you inserted an action, whether it will make the flow distribution among the nodes more uniform, and so on and so forth. So there are multiple types of interaction networks that can be considered for a more realistic description of food web. So these are some of the three approaches that I will present. One is the expanded food web, multi-layer, and equal footing. So for expanded food web, these represent the net flow of biomass or energy among the individuals, where the other layer of interactions may affect any parameter of the dynamical model. So here you have two layers, the solid network or system and the system represented by the dashed lines. Whereas for equal footing network, it's a multiple interaction network in which all interaction types are expressed in the same units. So basically, this is the same network shown earlier, but here, the interaction types are expressed in the same units for equal footing. Lastly, for the multi-layer network, it's a network with different types of connections between nodes. So in an ecological context, different network layers shown in the left side of the illustration is commonly represent different interaction types. So each layer represent different interaction types. This is a more interesting variation of or versions of multi-layer ecological networks. For example, in letter A, this is a temporal food webs. So the composition of the species actually changes in each layer with respect to time. Okay? Whereas in letter B, it's a spatial food web. It focuses on the spatial and temporal dissimilarities in species and interactions. So it also considers spatial aspect of the specific species in the said interaction. In letter C, you will notice that there's a shared species represented by the green nodes. So the network have actually different interactions. There's two layers, but there's a common or shared species in these two layers. And then in letter D, the nodes actually appear in every layer. So these are exactly the same nodes in each layer. But the difference is in each layer, the interaction is totally different to the other layer. Okay? But the nodes or the species in each layer has exactly the same number, or they are exactly the same. Okay? And then letter E, you have two layers, and then in these two layers, the species represented in these layers are actually unique or different. However, the species in one layer may affect or interact with the other species in the other layer. Okay, so this is interconnected. And then lastly, you can also represent the multi-layer using or represent it can also represent like a meta community. So each layer represents a community, and the nodes are the species in this community. So the species can have their own interaction in each community. However, it's also possible for a species like the node shown here, the yellow node shown here, it can actually disperse to a new community. So it can migrate to another community, and by moving to another community, it might have a different interaction weight with other species that is present in that community. So one may observe from this chart, so we have one that for structural and dynamical analysis, there's two track. Okay, you have the structural analysis and dynamical analysis. With whichever track we pursue, we observe that the multi-layer network is actually quite versatile, and most of the circumstances we actually multi-layer is an appropriate approach for different circumstances defined in this flowchart. So, and when you go into detail, we will also observe that this can also be applied to or can be satisfied by P-graph. So to give us an introduction of P-graph, I now give the floor to Dr. Tan.
Yeah, thanks very much. Good evening or good morning, wherever you happen to be in the world. My colleague, Dr. Angie, is in control of the slide, so I'll ask her to skip ahead to the next one. My role here this morning is to give the backstory of PGRAPH. PGRAPH has its roots in the field of chemical engineering, and I'm actually a chemical engineer by training. So if we go to the next slide, for those of you who are not chemical engineers, in the briefest definition of chemical engineering is that it's the branch of engineering dedicated to the mass production of chemicals. Very simple. And what differentiates chemical engineering from chemistry is that there's a lot of physics involved. And the reason for that is when you get to the stage where you mass produce chemicals, you begin with your raw materials. And typically at the heart of your industrial plant, you have a chemical reactor where the molecule that you want is formed. The problem is it's not going to be alone in the exit stream, but you need all of these downstream purification processes, because before you're able to sell that product at the price that you want, at the level that the market demands, you need all of these purification steps, such as you'd have distillation systems and decanters to separate fluid phases. And at the next level, you would need these industrial utilities to provide the energy that you need to provide heat for distillation and so on and so forth. So the problem in chemical engineering is you need to form the molecule and purify it to the level that is required by the market. The next slide, please. Within chemical engineering, there's a branch which is dedicated to computational techniques, which is known in the US as process systems engineering. In the EU, the alternative term is computer-aided process engineering, or CAPE. And it's in this area that I've worked for the past 2 decades. In this field, we have along the scientific value chain, at one extreme, we have the people who develop the algorithms and tools to solve specific kinds of problems. We like to think of ourselves as being higher up the value chain, so to speak. And of course, within the same spectrum of researchers, you would have people who use these algorithms and techniques to solve more specific industrial problems. And PGRAPH is one of the tools that was developed going back to the late 1970s over the past 4 decades. Okay, next slide, please. PGRAPH is the product of the collaboration between 2 of our colleagues. Ferenc Friedler came up with the mathematical foundations. He's based in Hungary. At one point in his career, he was based partially in the US. And in the 1980s and 1990s, he worked with L.T. Fun. The late Professor L.T. Fun is based in University of Kansas. Unfortunately, he passed away in 2014. But the 2 of them worked out the mathematical toolbox and how these tools apply to chemical engineering design problems. Next slide, please. Now, at the heart of the PGRAPH methodology is the bipartite representation of the processes that make up industrial plants. The bipartite representation is essential because it allows an unambiguous representation of how raw materials, intermediates, and products, which are material streams or M-type nodes, relate to the processes that make up the industrial plants. So these are operations, and these are known in PGRAPH terminology as O-type nodes. And what this means is if you have 2 operations in an industrial plant, they don't connect directly to each other, but they're linked by virtue of having common materials between them. So in other words, what that means is the output of one process becomes an input to the next process. And it's these kinds of relationships which can be represented very clearly through a bipartite representation. Next slide, please. Now, PGRAPH methodology is based on 5 axioms, which are shown on screen. I won't read through all of them, but as mathematical axioms should be, these are self-evident statements that provide the basis for the rigorous generation of algorithms for process network synthesis, which is the assembly of a schematic for your process plan. Next slide, please. The algorithms that were developed from those 5 actions are maximal structure generation, or MSG, solution structure generation, or SSG, and accelerated branch and bound, or ABB. In our work, we'll just use we've used so far just the first 2 of these algorithms, and I'll describe them in simplified terms in the next few minutes. Next slide, please. And I think it's better, rather than describing at the level of the algorithm, it's best to use a textbook toy case study. Okay, so if we go to the next slide, let's pretend that we have a design problem and that we're engineers working for a firm that is seeking to produce product A. And the product A is our main business, and the raw materials that we can purchase from the market, which are readily available, are E, G, J, K, and L. At the same time, let's say that the current state of technology, with the current state of technology, we have 7 processes which we can use. In other words, we could buy these process units from suppliers and assemble them into an industrial plant. And for instance, what we would see is in this diagram, process number 1 requires an input of material C to produce materials F and A. So process number 1 actually can generate the product that we need, which is A. The problem is the input required by process number 1, as you would see, is a material called C, which is not available on the market. So if we wanted to use product 1, we would actually need another process which would generate C as an intermediate. So essentially, you could take these building blocks of the process plant and represent them in the inset box. They're shown as process graphs. And the problem of the chemical engineer in what is known as process network synthesis is to come up with a general schema for the process plant. Even before we design the details of the pipelines and such, we need to figure out what is the sequence of steps that will convert any one of the raw materials that we can buy from the market to produce the product that we intend to sell. And believe it or not, even in this modern era, this process is actually done somewhat heuristically by teams of engineers. So we haven't gotten to the point where we can actually automate this process network synthesis process in regular chemical engineering practice. Now, how do we connect all of these options to give us what you might call as a master plan that contains every possible option? And in PGraph framework, this is known as the maximal structure. In the next slide, this is the maximal structure generation algorithm. We don't have time to go into the details, but you may wish to look at Ferenc Friedler's 1993 paper in Computers and Chemical Engineering for the description of the algorithm. In the next slide, what we would see is the product of MSG. Now, our example is actually simple enough because there are only 7 processes involved. You could actually, given a few minutes, you could work out all of the connections, all of the ways by which you can connect the process alternatives into a maximal structure. If you had a more realistic number of individual process units, say a couple of hundred of them, it would be an impossible task for a human to do this without the risk of incurring human error. And this is where the advantage of PGraph lies. By having an algorithmic procedure to take those building blocks and assembling them into a complete network for which there is mathematical proof that the connections are complete and that there are no redundancies in the system, we're actually able to generate a maximal structure which is sure to be correct. And there's some interesting examples of, or counterexamples using PGraph that showed previous solutions to be incorrect in terms of profitability by as much as 30%. But we'll move on to the next slide, because the next problem really is, if we have a maximal structure, which is defined as a structure that contains every possible or every combinatorially feasible design for a process plant, How do we then elucidate each of these candidate structures so that we can examine them, so the engineers can examine which ones are more profitable or more efficient? The next step is the solution structure generation algorithm, or SSG, which was developed in the late 1990s, or mid 1990s rather, also by Friedler and colleagues. This is the algorithm. The paper was published in Chemical Engineering Science. But what we'll do is we'll go from the maximal structure and see what happens if we examine every possible design that can be generated. So if we look at the next slide, from the structure that was shown originally, these are 7 candidate structures. All of these are structurally feasible. In other words, you can produce the product at hand from any of the raw materials that are actually available in the market. So here we have 7 candidates, but the candidates don't end here. If we go to the next slide, we have additional designs that we can choose from, 14 of them, but the list doesn't end there. In the next slide, we have then, by using SSG, listed down 19 possible network structures for our design problem. And what that means is any one of these network structures can then be the basis for developing a detailed plant design that satisfies the requirements of using the component technologies or processes, producing the desired product A, and relying only on raw materials that can actually be bought from the market. And there are 19 components here. It's significant that this suggests that SSG is able to avoid the combinatorial explosion, because we have 7 process units. 2 raised to 7 is 128. So potentially, if you were to comprehensively list down candidates, you might think you'd have 128. But we've narrowed down the list to just 19. And this scales up dramatically. For instance, one of Friedler's earlier works with 35 process units, which combinatorially would lead to 35 billion combinations if you were not to screen them for combinatorial feasibility. So 35 billion. But when he used SSG, they scaled it down to just 3,000 network structures. So that was scaling down the problem by a factor of 1 million for what was a medium-sized design problem. Okay, if we go to the next slide, those are MSGs and SSG algorithms. The key advantages of pGraph as a design tool, if we go to the next slide, essentially is that I mentioned earlier that design engineers even now use a heuristic approach and rely on engineering know-how. There's always the risk, even though a lot of times the heuristics actually work, there is still the risk of incurring human error. And there is a risk that design engineers, no matter how experienced they are, could miss very promising and very innovative designs. So what pGraph is able to do, by being able to enumerate every possible structurally feasible design, can actually discover counterintuitive designs with interesting features, such as those which are energy efficient. Next slide, please. And in terms of using pGraph, obviously we can say that by being able to enumerate the options available, it really provides effective decision support. We're able to list not just the best solutions, but those which are second best, third best, and so on. And in terms of convincing stakeholders, for instance, engineers would seldom actually be the end decision makers, but the company CEOs or politicians would be the end result decision makers. It's important to be able to be more persuasive. The analysts need to be more persuasive by being able to show the options to the ultimate decision makers. Next slide, please. Now, I'll move on to the last couple of minutes, current pGraph research landscape. And in the next slide, let me just say that Ferenc Friedler has put in a lot of effort since 2015 towards expanding the pGraph network. Last year, we had a paper published in Current Opinion in Chemical Engineering outlining some of the important, promising research areas. And in the next slide, for those of you who are interested in learning the basics of PGRAPH and actually using this for some of your research. There's a software hosted by the University of Pannonia. Our colleagues have been hosting this for many years. You can access the software free of charge via this website, pgraph.org, but you would have to register as a user. In the next slide, which is perhaps my last slide, I just want to say that the core PGRAPH team is currently based in Pázmány Péter Catholic University, which is in the heart of Budapest in Hungary. One of our co-authors, Heriberto Cabezas, who is an ex-US EPA, he used to work at the National Risk Management Laboratory. He retired a few years ago and joined PPKE as a professor. And when I was there back in October, our desks were next to each other, and we started chatting about the prospect of taking an engineering tool. And because he used to work with the EPA and he had some working knowledge of ecological networks, we struck up a conversation about how might we use PGRAPH, which was a design tool originally, as an environmental management tool dedicated to understanding ecosystems. And he asked me, do you know anyone who has working knowledge of this? I said, well, my colleague back home, Dr. Angelyn, has some work on biomathematics, essentially applying mathematics to various biological problems. So now we've come full circle, and we've started with ecology, and we've shifted somewhat abruptly to chemical engineering. But I think the lesson now is, with a bit of imagination, we can really take tools that were developed for one domain, and if you have a bit of creativity and imagination and a nice multidisciplinary team, you can imagine and develop novel applications. And that brings us back to the work at hand. How does PGRAPH apply to ecological network analysis? So back to my colleague, Angie, Dr. Angie.
Well, thank you. So motivated by all the works presented earlier, we now show the rich potential of PGRAPH to deal with the analysis of simple social ecological network model. So from the previous slides, from the literature, there are two challenges that are apparent, okay, on social ecological models. So the existing techniques assume that a single type of interaction predominates in the system. And then the other one is that most of the ecological network analysis gives a fragmented or one-dimensional representation of real ecosystems, wherein in the reality, components play multiple roles relative to each other. Thus, there's a need for a framework that allows concurrent modeling of these multiple roles and the resulting complex interactions. So this is the axioms presented earlier. We converted it into social ecological systems. So the terminology like final product for process engineering is converted as terminal ecosystem service in the social ecological system. The material is converted to ecosystem service. Raw material is an ecosystem service that is exogenous. And then operating unit is converted to the term functional units. So maybe let's briefly go through the 5 actions. In order for one to have a PGRAPH of a social ecological system, it has to satisfy all of these 5 actions. So the first one is there should be at least one well-defined terminal ecosystem service in the ecosystem structure. The second one, an ecosystem service represented in the structure is exogenous if and only if it is not an output of a functional unit defined in the ecosystem structure. And the third one, every ecosystem functional unit in the ecosystem structure should be well-defined. Any ecosystem functional unit has at least one path leading to the terminal ecosystem service. And lastly, if an ecosystem service belongs to an ecosystem structure, it must be an input to or output from at least one ecosystem functional unit represented in the structure. Here we illustrate the use of PGRAPH on socio-ecological systems by a case study. So the analysis shown here focuses purely on structural aspect and does not delve into the stream flow rates like what is presented earlier for ENA, for ecological network analysis. So as you can see in this illustration, energy enters in the ecosystem as sunlight and is captured in chemical form by photosynthesis like plants. And then the energy is then passed through the ecosystem. From plants, it's absorbed or consumed as food by the herbivore, okay? And the herbivore serve as a food for the carnivore. And then all of this will be decayed when they died, okay? However, in this illustration, you can also see that while the herbivore consumes the plant as a food, it also serves as a pollinator, okay, for the plants. Okay? And here in this model, we assume that herbivore and plants will serve as food for the human population. So this is a box diagram representation of the socio-ecological systems. We've actually further elaborated the socio-ecological system. So here we define specific characteristics of the plants and herbivores. So as you can see, we have 3 types of plants and 2 types of herbivores. For the plants, plant 1 here provide food for herbivore 1 and herbivore 2, and habitats for herbivores and the carnivores. Plant 2 also provide food for herbivore 1 and herbivore 2, and it contributes to the detritus. Whereas plant 3 contributes to the detritus and provides food for herbivore 2 and humans. As for herbivores, both herbivore 1 and 2 contributes to the detritus and provide food for carnivores. However, only herbivore 1 contributes to the pollination, and only herbivore 2 provides food for humans. So this is the assumption of our model. So this is the P-graph representation of the box diagram. This is also the maximal structure of the P-graph. So including the maximal structure, there are 20 different P-graph structures that are generated from the system. So these are all of them. And from all of those possible P-graph structure, this is the minimal structure. In the minimal structure, observe that plant 1, plant 3, herbivore 2, and carnivore are excluded from the system. So this is bare bone systems with the absolute minimum functional units that is necessary to produce the terminal service, which is food for humans. So this can also be summarized in table format, where the check marks actually pertains to the presence of the given functional units. So one may observe, interestingly, that for this particular ecosystems, carnivore is not essential in the sense that the rest of the ecosystem is capable of producing the terminal services, which is food for human, without carnivore. Okay, so this can be observed if you compare the structures pairwise. So the odd numbered structures contain carnivores, so there's a check mark for odd numbers structure, whereas the even numbered structure do not contain or do not have a check mark for the carnivores. So in other words, with or without carnivore, the ecosystem seems to still function. And this is because based on the defined socio-ecological system, if humans only eat plants and herbivores, then the existence of carnivore is not essential to make the system function. So for the plants, at least one of the plant should be included in the system. So this is what we generalize from the structures that are generated. So if 2 plants are to be excluded, so if we need to exclude 2 types of plant at the same time, we notice that it cannot be plant 2, okay? It can only be plant 1 and plant 3. So if you look at the illustration on the right side, if we remove plant 2 and plant 3 at the same time, this will directly affect the food provided for humans, okay? Because these are all interconnected to the terminal ecosystem service, which is the food for human. Whereas if you will remove plant 1 and plant 2 at the same time, it affects the food provided for herbivore 1. It also affects the habitat provided for herbivore and carnivore. Okay, so if we remove plant 1, plant 2, or plant 2, plant 3, this will all disturb or disrupt the sustainability of the system and the management of the ecosystem services. So in general, a functional ecosystem from our defined case study needs to allow the following. Okay? It should have at least one plant type. It should contain at least one herbivore type. It should also contain the soil microbes. However, if we go back to the table, we will observe that both herbivore and soil microbes are irreplaceable because all of the structures, the 20 structure, herbivore 1 and soil microbes are present in this 20 structure. And it actually appears to be crucial in the socio-ecological system because it can be explained by the important components it provides, which is the soil, nutrients, and pollination that is essential and needed by plants to grow and live. So basically, this ends our presentation. We'd like to thank the following funding programs, centers, and teams for supporting this study.
Okay, thank you very much, Angie and Raymond. So now we'll move on to the questions and some comments from our audience. So for those who have not been aware with the chat function of Zoom, so please feel free to type in any comments. So maybe I'll start with one of the questions on YouTube, in our YouTube watchers. So this is actually from Al Serafica. Can you model marine ecosystems like Raha Ampat, and how long for Anilao and Puerto Galera to be repopulated by sharks and rays?
I think it's possible.
Okay. Yeah, it's and another follow-up question from Al. This is directed to Raymond. Can you develop or use a P-graph for bamboo to make textiles for PPE and HEPA filters for COVID-19?
Good morning, Al. I definitely, for as long as the component processes can be defined. In other words, PGRAPH is a tool for designing an industrial plant under the assumption that the building block process units are technologically mature enough to put in a factory. And the problem of the designer is more which particular, for example, bamboo pre-processing units or processes do I buy, and how do I connect it to the next step, and so on and so forth. So the assumption is always like assembling a jigsaw puzzle from pieces that are well defined. So thanks for that question.
Okay, we have one question from Haobing Shen. I can get that forming a terminal service is the aim of the network, but he would like to know how the objective function is defined in PGRAPH. Raymond, I think you're muted.
May I respond to that? Well, Bing Shen, of course, Dr. Hao Bing Shen has worked with PGRAPH for his PhD. At the moment, the extent of our work has been limited to elucidating the combinatorially feasible structures. This is step one. And when we say marginally or just barely viable ecosystems, these are to say that the connections exist among the various components. We have not yet gotten to the stage of looking at the actual magnitudes of the flows. We have discussed these. For example, questions might be, if you have 1 million humans on an island, let's say if you have 30 million humans on an island like Luzon, where I am now, and the land area is so much, then you could conceptually define the maximum level of ecosystem services that you can generate from a specific land area. Or you could work out the opposite. You could minimize the land area needed to provide ecosystem services to support a human population. So the objective functions would probably eventually be some kind of ecological footprint variant, but that's still work in progress. We need to get the first paper through peer review because we got the reviews a couple of days ago. Thanks for that question.
Okay, so maybe just a follow up on the question of Hao Bingshen. So essentially, the initial work is on establishing the relationships between the different components of the ecosystem, and that the actual flows or quantitative relationships are yet to be determined. Is that correct?
Yes, that's correct.
Okay, thank you, and we look forward to those future papers from your group. Okay, we have another question from our YouTube channel. This is from Andres Argotti. So, excellent presentation. Have you implemented your ecological model on PGraph Studio?
Yes, it's actually generated from the PGraph Studio.
Okay, but this is using the SSG, right?
Yes.
Is that correct? Okay, so thank you. We have a question from Edsel. So these are very interesting ideas.
Oh,
What is the role of humans? It seems that we are only benefiting or consuming, but not really contributing to the system structure.
It can be extended by adding contributions of humans. So this is just a toy model because we just want to first try or proof of concept um, for the approach that we are approach that we are actually trying to do. So maybe in the future that can be added or designed or studied.
Okay. Angie, maybe I'd want your insights on this because you've already worked with ecological networks previously using other types of models, and now you've transitioned towards PGraph. So, what advantages have you seen about modeling ecological networks into the PGraph structure?
So what actually excites me by using PGraph is the structures that it can actually generate. So usually the problem in modeling is we don't know how small or how complex the model we should actually consider. Okay? But with the different possible structures that PGraph generated using SSG, um, we're able to stream down more essential structures that might be more meaningful. So we actually also thought of applying this approach to study gene regulatory networks. So actually in gene regulatory network, you also have this dilemma, which pathways or interactions include and which should not be included, or which are more dominant or more essential in the said system. So I think PGraph has a huge potential uh, to determine good topological structure network for systems that you are interested to study.
Okay, thank you. It's actually really interesting. Okay, one question from Benja. So, what values did we put in the price or cost, and how do you actually address the lack of empirical data later on? Yet somehow connected to the question of Hao Bingshen.
all right. May I respond to that?
Yes.
At the moment, in the current paper, the problem that we dealt with simply had to do with two issues. One is establishing connectivity, and the second is establishing the importance of the various components of the ecosystem based on how essential they are uh, by virtue of their connectivity to other components. So this was the objective. We have not gotten to the point of looking at the flows and the magnitudes of these flows. That is, of course, the next step in the work. Um, the reason for this is if you have an ecological network, the way biologists work, as I understand it, I'm not a biologist myself, but I have quite a number of biologist friends. Biologists work specifically on organisms. So there's plenty of localized knowledge on, for instance, if you were studying foxes, you would figure out their habitats and what they prey on, and who are their natural enemies and such. So there's plenty of localized knowledge on individual species and the components of ecosystems. And then someone else would be working on rabbits and would characterize rabbits in a similar way and thus the individual biologist would have a pretty good understanding of how the components of the system work. What PGRAPH, what we thought PGRAPH would be essential for, would be to take these bits of knowledge and assemble them into a coherent system without risk of human error. In other words, given the assumption that the knowledge provided by the biologists at the level of the organisms is correct and complete, then it is possible to deduce what the actual ecosystem network looks like at the global scale. In other words, once you figure out all of these interacting components, these are all the possible ways by which they interact in terms of who eats who, but at the moment without consideration of the actual magnitudes.
Okay, thank you for
incidentally, of course, we're happy to collaborate with anyone who's interested in this work. Perhaps even graduate studies might be forthcoming.
Okay, thanks. Okay, we have one question from Vince, Daria. So the P graph is a good graphical representation of the rate equations per process. For the specific model presented, how does the temporal evolution look like when running the simulation? How do the different variables behave as a function of time? Is there a pattern? Is it sinusoidal or something else? Yeah.
It is not time dependent, so it happens at the steady state.
Yeah, do you think it's possible to extend the model into like multi-period framework? Angie, I can't hear you. Okay.
Perhaps similar to what is presented earlier for multi-layer networks, you can have different layers of P graphs, and this different layer will corresponds to the time. Perhaps that's my.
So you have a lot of things after this, so many more papers. Okay.
I'd like to comment. May I comment on that very briefly? This is not my own work, but Ferenc Friedler and our other co-author, Akos Oros, who's his PhD student, they've done work on resiliency of engineering networks. In other words, if you have a network which is designed to perform a particular function, and then conditions change all of a sudden, very often, as you would see in economic networks, as a result of the current lockdowns all over the world, very often networks that are designed to perform one function under a given set of conditions would fail to perform once you change the boundary conditions. Now, they did this for engineering systems, but obviously because we're discussing the next steps in this process, we can also look at how ecosystems, which are in a sense optimized by evolution to meet current conditions. For example, certain prevailing climate conditions in the island of Luzon, for example. The problem is once you have disruptions like climate change or anyway, generally external disruptions which cause a change in the boundary conditions, the question is always, would your system, which was optimized for condition A, be able to survive a shift to a set of conditions B? Now, if you can do ecological engineering and sort of brace your system in anticipation of future disruptions, like if you were to expect in the next 20 years that, say, temperature in the Philippines would go up on the average by 2 degrees Celsius, in principle, it is possible to start figuring out should we shift crops from, in particular areas where farming is done, should you shift from particular variety of crops to some which anticipate future changes. So these are things which are very interesting and in principle can be solved with some network approaches. Thanks.
Okay, it seems like Melvin Kabatuan, who is actually watching us on YouTube, read your mind because his question is there a way to include environmental factors or the influence of events in the P-graph models, such as pandemics, natural disasters, and so on? Maybe I can add up to that. If such things happen, do you think it will be a change in the network structure? Would new links have to be established, or it's just changing the boundaries of the system?
let me take a crack at that. Firstly, with pgraph, we're able to do this typically when we have a discrete set of scenarios. Now, there is never any guarantee that a given network that works for current conditions would remain functional for a new set of boundary conditions. I mean, it could either by design or by accident. So the engineering problem here, in my view, the engineering problem is that you need to be able to anticipate what those alternative conditions are and then design today's system to be braced or to be ready for those anticipated conditions. And I think that's the best that can be done. I mean, you design a network and it may accidentally be able to withstand shifts that you were not able to anticipate. But as a matter of best practice, the engineering designer needs to map out likely conditions of operation and then design a system that can fit all of those. And this is the work that Ferry and Akos are doing now. Our challenge also is to take those and apply the same principles. This is my view. I've made a career out of analogies that the network principles cut across different domains. And I would say, just very briefly, pgraph was originally developed as an engineering design tool. People have scaled it down to the level where pgraph represents chemical reactions. That's in one direction, downwards. It's been scaled up as well to the point where I have a 2015 paper where we modeled entire economic systems of an entire country via pgraph. And of course, even before we started, we were talking about can we use pgraph for example, for artificial intelligence applications. So as long as you see networks and you have a bit of imagination, I think you can explore how that might work.
Okay, thank you for that. We have another question from Edsel. So since the models are deterministic, how do you see stochastic models fitting into this current framework or structure? So in addition, how about the role of game theory in the interactions such as in the Lotka-Volterra type models?
I think it's possible to integrate stochastic approach, but currently I think in the software or pgraph studio, it's not yet stochastic. The approach is not yet stochastic. And then for game theory approach, I'm not sure how game theory can be applied to that, because that might involve knowing how the interaction or defining the interaction between the species, maybe. But for now, the design of the structure of the network or the system is predefined first before you actually analyze it using pgraph.
Well, can I just, my rejoinder to Edsel's, thanks for that interesting question on game theory. I wish Joe Cruz was here to join the discussion as well. I started a bit of work with a colleague from New Zealand who's also done pgraph, Dr. Tim Walmsley at University of Waikato in New Zealand. And I began initial discussions on how we might use pgraph for cooperative games. And the notion we had was that we'd have companies represented by nodes, and they had to sign a contract as to how to share profits and how to share costs. And we thought pgraph would be a way by which they can have a rational basis for fair profit sharing. Unfortunately, the work has stalled a bit. I was planning to go to New Zealand, but they're not open to any visits from overseas at the moment. So we'll restart that work soon.
Okay, there's a follow-up from Edsel. So in this ecological network model, such as pgraphs, does nature find the optimal structure, or is nature efficient?
Nature.
May I, let me take my crack at this. Based on my experience with, about 15 years ago, I had a bit of a flirtation with swarm intelligence. I had a few papers on this, so I have some notion of how evolution works from a computational standpoint. Generally, natural systems are what I would define as near optimal. In other words, I don't think there's any rigorous, I may be mistaken. I don't believe that when a system evolves, for example, if you were using genetic algorithm to solve a problem, what you're seeking is a near optimum solution, which is good enough to pass for an optimal. So in that sense, I would say nature produces robust quasi-optimal solutions by virtue of evolution, simply because those which are not good enough don't survive.
Yeah, okay. And there's a further comment from Edsel. There is a book entitled End of Theory, which is advocating ABM. I suppose this is agent-based models. Okay, in the economic context, and seems to deal with these issues of dynamic changes. Okay, I have one question from Christina in the YouTube. Will you add human intervention in the ecosystem structure to determine its effects and impacts?
It's possible for future work.
So maybe just to clarify again, the current model that you showed, you mentioned that the carnivore, some of the structures do not require the carnivore to be present. But in the current model or framework that you showed, what purpose does the carnivore serve? Does it include providing food for the humans or no?
No.
Okay. Okay, thank you. Another question
I'm
from
sorry, Kay, may
yes,
I just
yes, sure,
add
sure.
in a little point to Christina's question? One of the things we think we would be able to do with the P-graph approach is to guide human interventions. And this could be whether it's positive or negative. For instance, there is plenty of work being done on what is known as biological control of pests. And essentially the intent is if there's a species which you don't like because they attack your crops, you could bring in a natural predator with the intent that you see a first order link. This particular insect preys on this insect which is devouring your crops. So it would seem, just looking at the first order interactions, that would help agriculture. Now, what that approach probably fails to look at is there may be roundabout indirect effects which are nth order, which are hard to see if you don't have a systems perspective. This is the sort of thing that a network approach would be able to do.
Okay, thank you for that. And we have a comment from Hao Bing Shen. So he can see how the creative use of P-graph, and it can solve lots of interesting problems when clear-cut objectives and the scopes are made. So he's looking forward to your future work soon. He also said that for stochastic modeling, probably Raymond and I think Raymond and Dominic have a paper to integrate the use of P-graph and Monte Carlo simulations, which probably can be implemented for this case as well. Coupling P-graph with other tools are another way out. Like P-graph helps to determine combinatorially feasible solutions effectively, then another tool can kick in to solve the problem.
So is there a software already that integrates stochastic?
No,
not yet. Maybe we can request Akosh and Ferry to do it.
Well, first of all, actually our host, Kay, is actually the third author of that paper that Bing Shen is referring to. Now, Ferry is always careful to say that we must not confuse the limitations of the software with the limitations of the algorithm. The software available is the product of R&D done in University of Pannonia. And of course, it has specific constraints because it's essentially used as an engineering design tool. So it's configured to solve engineering problems. but the algorithm itself. If you were to go out of your way and develop new software out of the same algorithm so that it's tuned and customized to solve a new set of problems, that can be done. And you just need to have a good enough programmer on the team to be able to make it work. And fortunately, of course, Angie and I, one of our co-authors, Akosh Oros, is a programming whiz with very good algorithmic mindset, and he's able to do the work. A lot of incidentally, the paper, once it gets published, for those of you in the audience, in addition to pGraph Studio, Akosh developed a Visual Basic implementation with an Excel interface. So anyone who wants to play around with small scale problems would eventually have access to this Excel file with which you can run small simulations. Okay, thank you again.
Okay, thank you. So I think I've exhausted all of the questions. Do you have any final thoughts, Angie or Raymond?
So this is a promising tools or modeling approach that can be used to study ecological systems and maybe to other biological systems like gene regulatory networks.
Well, perhaps one parting thought from me. Many years ago, I read this book, The Blind Watchmaker by Richard Dawkins, a well-known evolutionary biologist. And one of the quotes that I've taken away from his book, just to paraphrase, many scientific breakthroughs are based on somebody figuring out that this tool developed for this problem actually works for some other problem. And you can have one paper if you do that, and then find another problem, and that's another paper. So that has been a formula that I've made it work for myself. I'm happy to bring in colleagues and cooperate and develop new applications. I think that's a good way to propagate knowledge and develop new scientific knowledge. Thanks once again, everyone, and thanks to Dr. Angie and Dr. Kay for this morning's event. And those of you who gave your questions, much appreciated.
Okay, before we end, let me just plug our webinar for next week. So he's actually in the audience. So I hope you can see my screen already. So next week, we're having a lecture by Dr. Vince Daria. It's entitled Decoding the Computing Power of Neurons. So Vince is the one who established the Neurophotonics group within the ECLAS Institute of Neuroscience and is jointly affiliated with the Research School of Physics at the Australian National University. So if you want to join the webinar next week, so please register at bit.ly/vdaria. And for all those who are not part of PAASE, so I just wanted to tell everyone that you can find us on Facebook. So we have a Facebook account. We also have our website, which is paase.org. And all the webinars that we are conducting will be recorded and are uploaded in our YouTube channel, PAASE Webinars. So thank you. Thank you, everyone, for joining us this morning. And I hope to see you again next week. So that's it. Thank you, everyone.